In this series of video, we'll discuss about an important topic of constraint programming, which is modeling. And we will use a case study that is the bin packing problem for explaining some of the techniques that I use frequently and I think about when I have to model a problem in constraint programming. So first thing that I would like to say is that modeling is more an art than a science. So the goal here is to try to model a real-world problem, but of course you don't have the same expressivity as the real world because you are a little bit restricted by, for instance, the constraint programming technology, the library, the type of constraint that you have, the type of variables that you have. So the goal is to try to build something that is useful and try to find a model that is able to create solutions that correspond to the real world problem. And for same problem, if you ask two different modelers to come with a model, it's possible that they will create different types of model. They might choose different decision variables, they might choose different domains, different constraints. And depending on the model that you will create, it can have a dramatic effect on the solving time of your problem. So it's very important to think about the good way of modeling your problem in CP. So let's come back to my case study. It's a very simple problem to explain. That's why I have decided to explain that problem. But still, there are a lot of different techniques that we can use to make the solving of that problem more efficient. That's the bin packing problem. So in this problem, you are given n items. They are represented there. Okay, and each item has only one dimension, which is the size of the item. And we need to pack all these items into n different bins. Each bin has the same capacity, so they are completely equivalent. They all have the capacity C. Okay, and of course you need to decide for each item, for each object, in which bin you want to place them so that the capacity of the bin is not exceeded. So what are the decision variables that we can decide for this problem? There are two different points of views. The first one is the point of view of the item. You can decide for each item in which bin you would like to place that item. That's the first point of view. The second point of view is the point of view of the bin. In terms of bin, what you would like to decide is what is the set of items allocated to each bin. And which one should you decide? Well, these two points of view are good, but this one is still a bit more complex to model because you need a kind of set variables, and we don't have this kind of variable in mini-CP. It exists in constraint programming. Some people have invented set variables, but it's not ready in mini-CP. So we will go for this point of view because that's the one that we can use to model directly in mini-CP. So the decision variables, I will introduce one decision variable for each item. I will call it X, and it represents the identifier of the bin in which I will place the item. So for instance, if X0 takes the value 1, it means that this item will be placed into bin 1. So I have one decision variable for each item, but I also have one decision variable here for each bin. And this one, the L variable there, Lj, represents the height. So that's really the height, how much this bin is packed in terms of the total weight of the items allocated to that bin. Okay, and so the domain of the load variables, they go from 0 up to C, which is the maximum capacity. And in terms of the domain of the X variable, you give the set of all the possible bins. So that's one feasible solution to my problem. Okay, I have represented here the assignment of each of the variables, and these are the packing of each of the bins there. You see that they are stacked, okay, from the bottom to the top, and none of them exceed the capacities C, so that's a feasible solution. In terms of constraints, because I didn't so far express the constraint is that you should link the load variables and the placement variables. So what I will do is that for every bin, the load of this bin J, okay, the bin I use J for the indices of the bins and I use I for indices of the items. So the load of the bin J is the sum of all the items that are packed, that are placed into that bin. So I will do a sum there of the weight here of the item I, and this will be a 0,1 variable, okay? It will correspond to a 1 if the item xi is placed into bin j. Okay, if that equality holds, it means that it's a 1, And so in that case, you will contribute by an additional wi value to the load of the bin j. Okay. If it's a 0, of course, it means that you do not take into consideration the item I, and it has no impact on the total load for that bin. Okay, so that's a verified constraint, you know, that's a kind of verified constraint. And of course, the load variable, okay, they can go up to the capacity C because this is what was given in the domain, okay? We do not want to exceed the capacity C, but it can be a little bit less as well. For instance, for the bin 1 there, that you see, I do not reach the capacity C. I'm a little bit less loaded than the capacity C, and so the variable L1 will take a value that is less than C, less than the capacity bound. Okay, that's the model that I will write for the bin packing problem in MiniCP. So that's the input of the problem. So I've got the capacity, I've got here the weight of all the items. Okay, I get there the number of bins, so I'm allowed to use 5 bins, and I have here the number of items, that's just the length of this array. I create the solver, and I have the 2 variables there. The decision variables is the X array of variables. I create 1 variable for each item, and the domain is of course the set of bins. Okay, so from 0 up to number of bins minus 1. And for the load variables, as expected, it's between 0 and up to the capacity. Okay, that's why I have the capacity plus 1 there, because that upper bound that I give there is not included. Then I will introduce 1 variable, Boolean variable, that represents if an item I is placed into bin j. Okay, so that will be the I indices, and that will be the j indices. Okay, and so in bin, I call it in bin, this variable, in bin ji will be 1 if item I is placed into bin j. And so I need to compute that one, so I will use here my is equality constraint, my is equal constraint that you already know, and this is exactly what it's doing there. Okay, it's capturing here this 01 variable to say if item I is placed into bin j, then this variable should be true. Okay, this in bin ji should be true in that case. Okay, that will be linked by the is equal constraint. And so what I retrieved there, you see, it's a Boolean variable. But you already know that the Boolean variable we can use it as a 01 variable as well in because we extend also the integer variable with Boolean variables. Okay, and then once I have these Boolean variables that correspond to the placement of an item into a bin, I also need to multiply this one by the corresponding here weight, and this is what I'm doing there with the mul constraint. So I will multiply this Boolean variable by the weight of the item, and I will retrieve this one as wji. Okay, and so this wji will be either 0 or it will be equal to the weight of the item I. And then to link all these variables to the load variable of the bin j, I simply do the summation of all these wj variables. Okay, so I will simply do there the summation, and I will link that to the load variable of bin j. And then you can use a standard search because you only need to branch on the x variables. That's the placement decision variables that you need to fix. Okay, and I can use here a first heuristic, for instance, for the variable x, and you can use that model to find a feasible solution to your bin packing problem. That's a very basic formulation for the bin packing problem. What I will explain now is how to improve a little bit this model. First thing that I would like to say is that it's very common to model this kind of bin packing component inside problem in CP, and this is so frequent that people have invented a bin packing constraint for that, for modeling exactly this relation between the placement of items and some capacity. And the signature of the bin packing problem takes the load variables, the placement variables, and the weight of the items. Okay, and so in most of the solver you will find this very useful building block, which is called the bin packing constraint, or it can have different name. This constraint was introduced in these papers, and you can also find some filtering algorithm in my thesis about the bin packing constraint. The model that we have shown so far works perfectly well, but we can improve it, and we can improve it by adding redundant constraints. Redundant constraints have the property that they do not exclude any feasible previous solution that you have expressed with basic constraint, but they might improve a little bit the pruning of the search space by improving the communication between the constraints, for instance. So I represent the redundant constraint as this one, okay? So they improve the communication between, for instance, in bin packing, between the simple packing constraint of each of the bin. You will make them a little bit communicate better and detect, for instance, earlier inconsistency. So how do you find them? You find them by expressing new properties of the solution. So one property that we didn't use so far for the bin packing is this one. We can link the weight of all the items and the total sum of the load variables. And we can, for instance, express the fact that the sum of the loads variables is equal to the sum of the items that you need to pack. Okay, that's clearly true, but simply by adding the constraint, we will be able to catch failures that wouldn't be detected without it. Let's consider this example. So we have two bins there, and this represents the domain of that bin, of that load variable, and that's represent the domain of that load as well. We have already packed one item of weight 3 into the bin 0, and we have packed one item of weight 2 inside the bin 1. Okay, so if I use simply this constraint, I'm not able to detect any removal there. Okay, so there is no infeasibility per se. We can still pack individually each object there inside the respective bin. Okay, that constraint does not detect any problem. But with this redundant constraint, we will detect that the problem is infeasible. Look a little bit at the situation. So the sum of the load variables is between 3 and 7. Okay, we know that we have already packed 3, so we are at least loaded by 3. That's there, and we can go up to the capacity 7. For bin 1, we have already loaded 2, and we can go up to a capacity of 5. Okay, so if I sum these two ranges, we have a range that is between 5 and 12. That's fine, but if I sum all the weights of the items, I reach 14. And so is it possible that 14 would be inside this interval 5, 12? No, the answer is no. And so that's redundant constraint will detect that the problem is infeasible. We have not enough space to pack the remaining items given the empty space that is available at that time. Okay, so again, without the redundant constraint, we do not see this failure, but with the redundant constraint, we detect it. So for the bin packing problem, it's very easy to add this redundant constraint. You just need to add this line. You just need to add that the sum of the loads there is equal to the sum of all the items. So I simply here rely on the sum here of the in stream, the stream of all the weights of the items to compute it. So that's just a one line.